Hello there, and welcome to the Sleepy Space Channel. No human being has ever traveled to another planet. Not one. The farthest any person has ever gone is the far side of the moon, a 3-day trip made by 24 people more than a generation ago, and the dark beyond it has stayed empty ever since. Tonight we walk the road to each planet in turn and find what stopped us at every door, the sunward trap that makes Mercury harder to reach than the edge of the solar system, the furnace at Venus that no landing has ever survived, the return rocket for Mars that has never been built, the invisible radiation wall that guards Jupiter, and farther out, journeys so long they would consume the middle of a human life. 7 worlds, 7 refusals, and one quiet truth underneath them all. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of these distances is yours to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The farthest anyone has ever gone. The complete history of human travel beyond the Earth fits inside a sphere about 400,000 kilometers across. That is a strange and quietly sobering fact to begin with, and it deserves to be stated plainly. In all the decades that people have been flying into space, only 24 of them have ever left low Earth orbit. Half of that small company walked on the moon. Every other person who has ever flown, hundreds of men and women across generations of missions, has stayed within a few hundred kilometers of the ground. The great station that circles the Earth tonight orbits at roughly 400 kilometers of altitude. That is closer to the surface than many cities are to each other. The moon lies nearly 1,000 times farther out, and beyond the moon, no one has ever gone at all. This is the unresolved fact that sits beneath the title of tonight's journey. No human being has ever traveled to another planet. Not one. The record for the farthest any person has ever been from home belongs to a single crew who swung around the far side of the moon at a moment when the moon happened to ride near the far edge of its orbit. For a few quiet minutes, they were just over 400,000 kilometers from the Earth, farther from every other living thing than anyone before or since. That record has stood for more than a generation, and nothing flying today is capable of passing it. The dark beyond the moon remains, for our species, an unvisited country. The lunar journeys themselves were brief, almost beyond believing. Each crossing took about 3 days, the length of a long weekend. The crews carried everything they needed with them: air, water, food, power, and the propellant to come home, all packed into a vehicle whose living space compared fairly to a large closet. They could travel so lightly for one reason only, which is that the trip was short. 3 days out, a few days there, 3 days back. The pantry problem, the radiation problem, the problem of a human body slowly loosening in weightlessness, all of these were present even then, but the journey ended before any of them could matter. That is the quiet secret of the moon landings. They succeeded, in part, because they were over quickly. Against the distances of the planets, that record journey collapses into almost nothing. Consider the near neighbors first. At its closest approach, Venus passes within about 40 million kilometers of the Earth, roughly 100 times the distance to the moon. Mars, at its very friendliest, comes within about 55 million kilometers, which is close to 140 times the lunar distance. And these are the nearest planets, at their nearest moments, which arrive only briefly and only every year or two. Jupiter never comes closer than about 600 million kilometers, some 1,500 times the moon's distance. Neptune, the outermost planet, never approaches nearer than about 4,300,000,000 kilometers. If the journey to the moon were a single step off a front porch, The journey to Mars at its kindest would be a walk of more than a city block, and the journey to Neptune would be a walk of several kilometers into the dark, every step of it carrying your own air, your own water, your own warmth. There is a second way to feel the size of the gap, and it uses light itself as the measuring rod. Light is the fastest thing there is, and it crosses the space between the Earth and the Moon in about 1¼ seconds. Every crewed mission in history has taken place inside that little bubble, a bubble in which a question asked by radio and the answer to it fit together into a span of about 3 seconds. A crew near the Moon could speak with the Earth almost naturally, with only a polite pause between voices. Light needs minutes to reach Mars, and sometimes as many as 24 of them. It needs tens of minutes to reach Jupiter and Saturn. It needs roughly 4 hours to reach Neptune. To travel to a planet is to leave the bubble of conversation permanently, and with it, any possibility of real-time help from home. The voice of the Earth becomes a letter. The crew becomes, in every practical sense, the only people in existence. It helps to translate these distances into more familiar machines. A commercial airliner, flying at its ordinary cruising speed and never stopping, would need about 17 years to cover the distance to Mars at its closest approach. The same airliner would need more than 500 years to reach Neptune. The fastest object our species has ever launched, a small robotic probe that uses the sun's own gravity to whip itself along, moves at nearly 200 kilometers per second at its swiftest, and even at that speed, the outer solar system remains a journey of years. Crewed vehicles travel at a small fraction of such speeds. The ships that carried people to the Moon coasted most of the way at about 1 kilometer per second. Distance, in space, is not an inconvenience. It is the landscape itself, and it is nearly all there is. And yet the strangest part of the story is not the size of the gulf, but the thinness of our presence at its edge. Add up every hour that every human being has ever spent beyond low Earth orbit, every lunar crossing, every orbit of the Moon, every moonwalk, and the total comes to a matter of weeks. A single crew member aboard the station today will spend more time in space on one ordinary rotation than our whole species has spent, combined, in the deep space beyond our own orbit. More people have stood on the summit of the highest mountain on Earth in one busy climbing season than have ever left low Earth orbit in all of history. We speak of ourselves, sometimes, as a spacefaring species. The honest accounting is gentler and stranger. We are a species that has waded to its ankles, once, and has been standing at the shoreline ever since, looking out. There is one more comparison worth carrying forward into the night, because everything that follows will rest on it. The crews who flew to the Moon could abort their journey at nearly any moment. Their path was designed so that, if the ship failed, the Moon's own gravity would swing them around its far side and sling them home without a single engine burn, a free return written into the geometry of the orbit itself. One damaged crew famously rode exactly that path back to a safe splashdown. No such kindness exists on the road to a planet. An interplanetary trajectory is an orbit around the Sun, and once a ship is committed to it, the Sun sets the schedule. There is no turning around, because there is no around. There is only the long curve of the orbit, which will bring the ship home when the mathematics allow it, and not one day sooner. Every journey we will trace tonight begins with that surrender. The travelers hand their return date to celestial mechanics before they leave, and the solar system holds it, patiently, for months or years or decades. The machines tell the same story from the other side. Every robotic probe ever sent to a planet has been a small and frugal thing, lighter than a small truck, often lighter than a car, needing no food and no air and no promise of return. That is why the probes have succeeded everywhere. A crewed ship bound for even the nearest planet is a different order of object entirely. Once the life support is counted, and the water, and the shielding, and the propellant to come home again, the estimates in study after study settle in the hundreds of tons, a vessel that would have to be assembled in orbit, piece by piece, across years of launches, before its journey could even begin. The gap between a probe and a person is not a matter of degree. It is the difference between mailing a letter and moving a house. So this is where our species actually stands. 24 people to the edge of the bubble, and no one beyond it. Tonight, we will go beyond it, gently, and only in the mind. We will walk outward from the sun, planet by planet, and at each world we will ask the same two questions. What would the journey there truly demand of the people who attempted it? And why, after all this time, has no one ever succeeded? The answers are different at every planet, and each one is stranger than the last. But they all begin in the same place, with the price of leaving the Earth at all. That price is where we turn first. Part 2. The price of leaving. Every journey to every planet, no matter the destination, begins by paying the same 3 tolls. The first is the climb out of Earth's gravity. The second is the long change of orbit around the Sun. The third is the waiting for the right moment to go. These tolls are collected before any planet's own particular difficulties even enter the story, and together they explain more about why no one has succeeded than anything waiting at the far end. So before we visit a single world tonight, we should walk slowly through the price of leaving, because every world we visit afterward will present the same bill, only larger. The first toll is orbit itself. To circle the Earth just above its atmosphere, a ship must be moving at nearly 8 kilometers every second, a speed at which the whole of a continent slides past in minutes. Reaching that speed, when the losses of climbing and air resistance are counted, demands what engineers call about 9.5 kilometers per second of velocity change. That single number is the reason rockets look the way they do. A vehicle standing on the launch pad is more than 90% propellant by weight. The shining machine on the pad is, in truth, a thin metal skin wrapped around a lake of fuel, with a small cabin balanced at the very top like a thimble on a grain silo. Nearly everything a rocket lifts, it lifts in order to keep lifting. Behind that strange proportion sits a rule often called the tyranny of the rocket equation, and it is worth feeling clearly because it governs every journey in tonight's story. A rocket moves by throwing part of itself backward. The propellant it burns late in the flight must be carried by the propellant it burns early in the flight, which means fuel must be spent lifting fuel, which itself was lifted by more fuel below it. The cost does not add up. It multiplies. Ask a ship for a little more speed, and you need a somewhat bigger ship. Ask it for twice the speed, and you may need 10 times the ship. The demand grows exponentially, like interest compounding against the traveler, and there is no appeal, because the rule comes from the conservation of momentum itself. Chemical engines, the finest we have ever flown with people aboard, push their exhaust out at around 4.5 kilometers per second at their theoretical best. That number is the ceiling of the whole enterprise. Every mission profile, every launch window, every year of coasting silence in the outer dark traces back to the modest speed at which burning chemicals can throw themselves backward. The second toll is the transfer, and it begins with a correction to the picture most of us carry. A spacecraft bound for another planet does not fly toward that planet. It cannot, any more than a thrown ball can fly toward a bird in flight. The planets are moving targets, sweeping along their orbits at tens of kilometers every second, and a ship does not chase them. Instead, it leaves the Earth and enters its own orbit around the Sun, a long, curved, unpowered path, shaped so that it will cross the target planet's orbit at the exact place and moment where the planet itself will be. The engines burn near the beginning, briefly, and then fall silent. For almost the entire journey, the ship simply coasts, falling along its ellipse, the way a stone falls along its arc, while the solar system slowly rearranges itself around the path. The cheapest such path is a gentle ellipse that touches Earth's orbit on one side of the Sun and the destination's orbit on the other. It is the slow road, and it is slow in a way that surprises people. The gentle road to Venus takes around 4 months. The gentle road to Mars takes 6 to 9. The gentle road to Jupiter takes nearly 3 years, and the roads beyond stretch to 6 to 10 to more. These times are not failures of engineering. They are the shape of gravity itself, the natural pace of an object falling freely around the Sun. The journey can be hurried. A harder burn at departure flattens the curve and shortens the trip, but every hour saved is bought with the exponential currency of the rocket equation, and the price of haste climbs so steeply that even the boldest mission designs hurry only a little. There is a quiet detail hidden in the transfer that rewards a moment of attention. Because the path is an orbit and not a pursuit, the target does not actually matter to the ship. If Mars were somehow absent when the ship arrived at the crossing point, nothing dramatic would happen. The ship would simply continue along its ellipse, swing out to where Mars's orbit lies, curve back inward, and return to the place where Earth's orbit sits, with the Earth by then long gone around the Sun. It would repeat that loop indefinitely, a letter circulating forever between 2 addresses with no one home at either. Interplanetary travel is the art of arranging for someone to be home. All of it, every window, every burn, every year of waiting, is choreography, timed against the clockwork of the planets. Which brings us to the third toll, timing. Because the ship must arrive where the planet will be, departures are only possible when the geometry is right, when the Earth and the destination stand in the correct arrangement around the Sun. These arrangements are called launch windows, and they open on the planet's schedules, never on ours. For Mars, the window comes once every 26 months. Miss it by a week, and the mission waits more than 2 years for the next chance. For Venus, the cycle runs about 19 months. For Jupiter and the worlds beyond, windows recur roughly every 13 months down to about once a year, because the outer planets crawl so slowly that the Earth's own year sets the rhythm. A window is not a single day but a short season, usually a few weeks wide, inside which the cost in propellant shifts from merely enormous to briefly affordable and back again. Mission planners map those costs on charts whose curved contours resemble the marbling of a cut of meat, and they aim for the tender center. And for the grandest journeys, the windows grow rarer still. A ship can steal speed from a planet it passes, sweeping close behind a moving world and borrowing a little of its orbital motion, leaving the planet slower by an amount far too small to ever measure. This borrowed speed, called a gravity assist, is the only free gift in all of spaceflight, and the outer solar system is effectively closed without it. But assists demand that the lending planets stand in the right places, and the great alignments have their own calendars. The arrangement that once allowed a single probe to visit all 4 giant planets in one continuous flight occurs only about every 175 years. Some doors in the solar system open once in a lifetime. Some open once in 2. There is a 4th toll, collected at the far end of the journey, and it is the one most often forgotten. Arriving is not the same as getting there. A ship that has fallen across 500 million kilometers toward Jupiter arrives moving many kilometers per second faster than Jupiter itself, and if it does nothing, it simply sweeps past and returns to the dark. To stay, it must slow down, and slowing down is a burn like any other, paid in propellant that has been carried across the entire solar system at compounding, exponential cost. The alternative is to skim the destination's atmosphere and let friction shed the speed, a maneuver in which the corridor between capturing and burning is thin, and which, in its single-pass form, has never once been attempted by any spacecraft, robotic or otherwise. Every orbiter humanity has ever placed around another world braked with its engines, or trimmed its orbit with hundreds of cautious, shallow passes spread over months. And a crew, unlike a probe, must pay every one of these tolls twice. The climb, the transfer, the window, the arrival, all of it must happen again, in reverse, from a world with no launch pads, no factories, and no one waiting to help. When people speak of the difficulty of reaching the planets, this is the arithmetic beneath the words. The journey out is merely half the price. It is the round trip that has, so far, always been too expensive, and the reasons why grow clearer at every world we will visit tonight. But the tolls of physics are only half the bill. The other half is collected from the travelers themselves, and it is time to look at what the crossing does to a human body. Part 3. The body in transit. The second half of the bill is collected from the travelers themselves, and it cannot be paid with a larger rocket. A human body in deep space is running down several clocks at once, and every planetary journey must be finished before the fastest of those clocks runs out. The physics of the transfer decides how long the journey must take. The biology of the crew decides how long a journey may take. The whole history of crewed spaceflight beyond the moon, which is to say, the history of missions studied, planned, and never flown, lives in the gap between those two numbers. The first clock is radiation. The Earth shelters its surface beneath two great shields, a deep atmosphere, which absorbs incoming particles as surely as several meters of stone, and a magnetic field, which sweeps charged particles aside before they ever reach the air. A crew in low orbit still lives mostly inside the magnetic shield. A crew bound for a planet leaves both shields behind within hours of departure, and from then on, the sky arrives unfiltered. Out there, a slow rain of galactic cosmic rays falls from every direction at once, the nuclei of atoms, flung to nearly the speed of light by ancient stellar explosions elsewhere in the galaxy, traveling for millions of years before passing, by chance, through a ship and through the people inside it. The dose from this rain runs to roughly a millisievert a day, several hundred times the pace of life at sea level. Over a 6-month crossing, it accumulates into a meaningful burden. Over a multi-year round trip it approaches and can exceed the lifetime allowance set for professional crews. Cosmic rays carry a further unkindness. They are nearly impossible to stop. The particles are so energetic that when they strike a thin metal hull, they do not politely halt. They shatter, throwing off sprays of secondary particles that can be more damaging than the original ray, so that a lightly armored ship can be, strangely, worse than an unarmored one. Meaningful protection comes only from bulk, thick layers of water, of plastic, of food and stores and waste, meters of something between the sky and the skin. And bulk is mass, and mass is the one thing the rocket equation forbids. So every deep space design compromises in the same way. The ship as a whole stays thin, and somewhere in its middle, wrapped in the water tanks and the pantry shelves, there is a small, dense refuge, a storm shelter, sized for the second kind of radiation. Because the steady rain is only the background. The sun, a few times in every cycle of its activity, erupts, throwing off storms of particles that would deliver, to an unsheltered crew in deep space, sickness in hours. The shelter answers that danger, but it must be reached in time, and the warning comes from instruments watching the sun from near the Earth. The farther the ship travels, the older the warnings grow, and the more the crew must simply watch the sun themselves and judge. The second clock is weightlessness, and it is the stranger one, because it feels like nothing at all. A body in free fall is a body relieved of every load it has carried since it first stood up, and the body, sensibly, economical as always, begins to dismantle what it no longer needs. Bone dissolves at roughly 1 to 1.5% of its mineral density per month in the load-bearing skeleton, the hips and the spine quietly lightening, month after month, at a pace that turns a multi-year voyage into the skeleton of advanced age. Muscle wastes despite hours of daily exercise. The heart, relieved of the work of lifting blood against gravity, softens and shrinks like any idle muscle. Fluids drift headward, faces rounding, sinuses filling, and behind the eyes, in a significant fraction of long-flight crew, the pressure slowly reshapes the optic nerve and flattens the back of the eyeball itself, blurring vision in ways that do not always fully return to normal. The immune system dulls. The sense of balance, no longer needed, recalibrates so completely that the returning body must relearn the ground. Crews coming home from 6 months in orbit are lifted from their capsules by ground teams and carried to chairs. They stand again within days and recover within months, because the Earth is there to catch them, with its doctors and its gravity and its time. Now carry the picture outward. A crew arriving at a planet after 6 or 9 months of freefall arrives in the weakest condition of the entire mission, at precisely the hour the mission needs them strongest, the hour of navigation, of arrival, of the most difficult flying of their lives, with no ground team waiting anywhere in the world below. The longest single stay any human has ever made in weightlessness is about 14 months, undertaken once, in orbit, with home 20 minutes away. Every planetary round trip in tonight's story, except the briefest flyby of Venus, is longer than that record. Most are several times longer. The experiment has simply never been run, and the first crew to attempt a planet will be running it on themselves. The third clock is the pantry. A human being consumes, each day, close to 1 kilogram of oxygen, several liters of water, and nearly 2 kilograms of food, and produces, each day, carbon dioxide that must be scrubbed, water vapor that must be caught, and waste that must be managed. On a 3-day lunar crossing, the sums are luggage. On a 3-year planetary round trip, for a crew of 4 or 6, they are tens of tons, a warehouse, launched at exponential cost before a single instrument or tool is loaded aboard. The answer, everyone agrees, is recycling, and the recycling machines that exist are quiet marvels. Aboard the station, most of the water a crew drinks has been drunk before, recovered from breath and sweat and urine, distilled and filtered, and drunk again. But most is not all. The loops recover a large fraction and lose the rest, steadily, to filters and residues and imperfect chemistry, and the machines themselves demand a constant diet of spare parts ferried up from the Earth. No life support loop ever flown has closed tightly enough to run for years without resupply. A planetary ship needs exactly that, a sealed ark in which air becomes breath and breath becomes air, indefinitely, without a supply ship ever knocking. That ark does not yet exist. The 4th clock ticks in the mind, and the 5th in the space between the ship and home. As the ship recedes, the radio delay stretches, seconds, then minutes, then tens of minutes each way. Conversation with the Earth dies somewhere past the Moon's distance, not from any failure of equipment, but from the speed of light itself. Mission control becomes a correspondent. Family becomes a recorded message, answered by a recorded message. The crew of a planetary ship will hear, eventually, only each other, the same few voices, in the same few rooms, for years, sealed inside a hull beyond which there is nothing alive for millions of kilometers in every direction. Volunteer crews sealed in habitats on the ground, rehearsing exactly this, have frayed within a year, even knowing the door was real and could be opened. And beyond the psychology stands the plain operational fact that shapes everything. Past the Moon, there is no rescue. No resupply can catch the ship. No early return exists, because the orbit is the schedule and the sun does not renegotiate. Whatever breaks, the crew repairs or lives without. Whoever sickens, the crew treats, with the medicine in the cabinet and the training in their hands. Every mission plan for the planets arrives, eventually, at the same quiet sentence. The crew must be its own world, its own hospital, its own workshop, its own farm, its own government, for as long as the journey lasts. There is one remedy that would quiet several of these clocks at once, and it deserves a mention before we travel. Spin the ship, and the floor pushes back. Centrifugal force becomes a gentle counterfeit of gravity, and the bones and the heart and the eyes are given their work again. The physics is simple enough for a student's notebook. The engineering is not. A spin slow enough for comfort demands a radius of tens to hundreds of meters, a ship the size of a stadium wheel, or two cabins swinging on a long tether, larger than anything ever assembled in space. Like so much in tonight's story, artificial gravity is not impossible. It is merely enormous, and enormity, under the rocket equation, is its own kind of impossibility. These are the clocks, then, the dose, the bones, the pantry, the mind, and the silence. None of them stops a journey outright. Together, they set a limit on how much journey a human being can carry, and now, with the price of leaving and the price of enduring both in hand, we can finally begin to travel. We will go inward first, toward the sun, to the little world that by every map should be the easiest to reach, and is in truth among the hardest of them all. Part 4. Mercury, the Sunward Trap. We begin with the planet closest to the sun, and with an intuition that nearly everyone shares. On the maps we grew up with, Mercury sits just inside our own orbit, third door down toward the light. Falling toward the sun feels as if it should be the easiest journey of all, downhill the entire way, with the greatest gravity in the solar system pulling the traveler helpfully along. The intuition is exactly backwards. Falling sunward is one of the most expensive journeys the solar system offers, and Mercury is, by the strange accounting of orbits, arguably harder to stop at than the edge of the solar system is to leave. Measured in the velocity change required, a ship can escape the sun's gravity entirely for less than it costs to settle into orbit around the innermost planet. The problem is speed, specifically the speed we already have. The Earth does not sit still at the center of anything. It moves along its orbit at about 30 kilometers every second, and every ship that leaves it inherits that motion in full, the way a passenger stepping off a train inherits the train's speed. To travel outward, away from the sun, that inherited speed is a gift. The ship simply adds to it and climbs. But to travel inward, the ship must first get rid of the gift, must cancel away a great fraction of the 30 kilometers per second it never asked for, because as long as it carries Earth's speed, it will simply continue to orbit where the Earth orbits, forever. And cancelling speed, in space, costs exactly what gaining speed costs. There are no brakes to squeeze, no road to drag against. Slowing down is a burn like any other, paid in propellant at the rocket equation's compounding rates. The listener drifting towards sleep may hold the picture gently. The hardest part of falling toward the sun is convincing the universe to let you fall at all. And the falling, once begun, makes everything worse. A ship that sheds enough speed to drop inward begins to accelerate, as everything does when it falls. By the time it crosses the orbits of Venus and approaches Mercury's neighborhood, it is moving far faster than when it left home, and there, waiting for it, is a small, quick planet with almost nothing to catch it. Mercury sweeps along its orbit at an average of about 47 kilometers per second, the fastest of any planet, on a track more oval than any other, so that the aim point is not only swift, but forever changing its distance from the sun. And Mercury offers no atmosphere to brake against. Its so-called air is a vacuum by any human standard, a thin haze of atoms knocked off the surface by sunlight and wind, so sparse that its particles almost never touch one another. At Mars, at Venus, at the giant planets, an arriving ship can let an atmosphere shed some of its speed. At Mercury, every single kilometer per second of the approach must be cancelled by engines, with propellant hauled down the sun's gravity well at prices that multiply all the way. The robots have shown us what the journey honestly costs. A direct transfer to Mercury is short, about 3.5 months, the quickest planetary crossing there is. But a ship arriving on that path arrives hopelessly, unstoppably fast. So the probes that have actually reached Mercury orbit did not fly there directly. They spiraled inward for 6 and 7 years, braking the only affordable way, by flying past planets. One mission threaded 6 planetary encounters before it could fall into orbit, flybys of the Earth, of Venus, of Mercury itself, each pass trimming away speed that engines could never afford to cancel. Hold that number for a moment, because it is one of the strangest in tonight's story. The journey to the innermost planet, flown properly, takes longer than the journey to Jupiter. The nearest door to the Sun is reached by the longest hallway. Now imagine a crew on that hallway. Every month of those years is spent falling closer to the Sun, and the Sun grows without mercy. At Mercury's distance, sunlight arrives 6 to 10 times more intensely than at the Earth, and the entire logic of spacecraft design turns inside out. The problem is no longer keeping a distant, cold ship warm, but keeping a ship inside an oven cool. Radiators grow larger than the cabin they serve. Sunshades become structure. And the solar storms we met earlier in the night, the eruptions a Mars-bound crew would shelter from, arrive here at point-blank range, several times stronger, with the least warning anywhere in the solar system. Mercury itself offers no help. Its iron heart generates a magnetic field about 1% as strong as the Earth's, far too weak to shelter anyone standing beneath it. Suppose the crew endures the hallway, cancels the speed, and stands at last upon the surface. What they find is a world of magnificent, uninhabitable extremes. With no atmosphere to carry warmth from day to night, the two sides of Mercury live in different centuries of temperature. The sunlit ground climbs to about 430 degrees Celsius, hot enough to melt lead and tin, so that a bar of solder laid on the noon rocks would soften and run like wax. The night side, meanwhile, radiates its heat away into the black and falls below -170. And the day itself is a trap of patience. Mercury turns so slowly, locked by the sun's tides into a gentle 3-to-2 rhythm between its spin and its orbit, that a single day there, one sunrise to the next, spans about 176 Earth days. A crew that landed at dawn would wait 3 Earth months for noon. From the surface, the sun hangs 3 times wider than it looks from home, and near the planet's closest approach, it performs a slow, stately strangeness found nowhere else. It pauses in the sky, drifts backward for a time, and then resumes, on some horizons rising, dipping back below the edge, and rising again, a double dawn over a world with no one to see it. Only at the poles does Mercury soften, and it softens into paradox. Because the planet stands almost perfectly upright, its axis barely tilted at all, the floors of certain polar craters have never once faced the sun. Sunlight has not touched them in perhaps billions of years. In those bowls of permanent shadow, colder than the surface of Pluto, spacecraft have found the signature of water ice, frost sleeping a few meters from horizons of lead-melting stone. If humans ever do stand on Mercury, it will be there, in the dark rims of the polar craters, with the sun forever hidden below the edge of the world and the ice underfoot older than the continents of home. It is worth noticing, too, that this journey never gets cheaper by waiting. For the outer planets, patience buys alignments, and alignments by years of saved travel. For Mercury, there is no such season. The cost of the sunward road is set by the Earth's own orbital speed, the 30 kilometers per second that every departing ship carries like an anchor, and that speed is the same in every month of every year. There is no clever window in which the anchor weighs less. The hallway to Mercury is long in every calendar that will ever be printed. But no one is coming, not for a very long time. No crewed mission concept for Mercury has ever advanced beyond a sketch, and the reasons stack without pity. The velocity budget alone sits beyond chemical propulsion carrying human-sized masses. The slow, fly-by-breaking road the robots ride, 6 or 7 years each way, cannot be asked of a crew in that heat and that radiation. And the destination at the end offers no water but the hidden polar frost, no air, no shelter, and no reward that a machine cannot collect more safely. Mercury is, by a wide margin, the planet least likely ever to feel a human footstep, not because it is far, but because it is deep. It lies at the bottom of the brightest hill there is, and the hill only goes down. So we climb gently back up, away from the light, to the world next door, the planet that is closest to the Earth of all of them, the easiest to reach by every measure of the journey, and the one place in the solar system where arriving means nothing at all. Part 5. Venus, the nearest world, with no harbor. Venus is the planet that should have been first. It is the closest planet to the Earth, passing within about 40 million kilometers at its nearest, nearer than Mars ever comes. It is the easiest planet to launch toward, with windows that open every 19 months, more often than the windows to Mars. And it is the fastest planet to reach. The gentle road to Venus takes roughly 3.5 to 5 months, a noticeably shorter crossing than the 6 to 9 months the road to Mars demands. On the pure arithmetic of the journey, distance, time, propellant, opportunity, Venus wins on every line. If the solar system were judged from a departure lounge, Venus would have felt a human footfall generations ago, and tonight's episode would open there. The early planners knew this arithmetic well, and they took it seriously. In the first era of crewed spaceflight, when the great moon rockets were new, serious studies proposed sending a crew past Venus, not to land but to fly by, sweeping close over the cloud tops and coasting home. The mission had a deep elegance, and the elegance was gravity itself. The trajectory was a free return, a path shaped so that after departure, the geometry alone would carry the ship around Venus and back to the Earth, with almost no further propellant at all. One great burn near home, and then a year of falling, outbound in 4 months or so, a few precious hours in Venus's neighborhood, and a long, quiet coast back. The rockets to attempt it existed. The navigation was within reach. Of all the crewed planetary missions never flown, the Venus flyby is the one that came nearest to being real, and no law of physics stood in its way. What stood in its way was the destination, because Venus, examined closely, is a journey with no arrival. It is worth remembering how recently we learned this. For centuries, Venus hid its surface beneath an unbroken sheet of cloud, and people filled the blank sensibly, a world nearer the sun, wrapped in white, surely warm, perhaps wet, possibly green. Then the first robotic visitors arrived, and the imagined jungles evaporated in a single measurement. The surface of Venus rests near 460 degrees Celsius, hotter than the daylight side of Mercury, despite standing nearly twice as far from the sun. The heat is the atmosphere's doing. Venus wears a blanket of almost pure carbon dioxide, so massive that it presses on the ground with 92 times the pressure of Earth's air, the pressure our oceans reach about 900 meters down. Sunlight filters in, warms the rock, and the blanket refuses to let the warmth leave. There is no cool season, no mild pole, no gentle altitude on the ground, nowhere on the entire surface to stand. The planet is one continuous furnace, from horizon to horizon, day and night alike. The robots that have touched that surface tell the story in the plainest terms. They were built like diving bells, armored in titanium against the crush, chilled before entry so they would begin their descent already cold. They drifted down through the clouds, landed on plains of dark volcanic stone, and sent home the only photographs that exist of the ground of Venus, a flat orange world under a sky the color of dim amber. And then, one by one, in 20 minutes, in an hour, in 2, they went silent as the heat soaked through their armor and cooked their circuits. Nothing built by anyone has ever survived a full afternoon on Venus. No sample has ever been lifted home from its surface. And for a crew, the arithmetic ends before it begins. An ascent rocket, a machine of pumps, propellants, and thin-walled tanks, would have to survive the furnace and then launch itself through 92 atmospheres of resisting air. No engineering study has ever closed that problem. A landing on Venus is not a hard mission. It is not a mission at all. And yet Venus keeps one consolation, and it is among the strangest facts in the solar system. Climb. 50 kilometers above the furnace, the atmosphere has thinned and cooled through every intermediate world, and in a band around 50 to 55 kilometers of altitude, conditions become almost gentle. Pressure near 1 Earth atmosphere, temperatures between roughly 0 and 60 degrees Celsius. It is, by those two measures, the most Earth-like environment anywhere beyond the Earth itself, more temperate than any surface on any world we will visit tonight. Stranger still, in that heavy carbon dioxide sky, ordinary breathable air is itself a lifting gas. A vessel filled with the very air its crew breathes would float there, the way a helium balloon floats at home. Mission concepts have imagined exactly that. Crude airships the size of athletic fields, drifting through the high clouds of Venus, their lift provided by their own atmosphere, their crews living in the one narrow story of the solar system, where a human habitat needs neither pressure hull nor furnace armor. But the balcony has its own teeth. The clouds an airship would sail among are not water. They are droplets of concentrated sulfuric acid, a mist that etches metal and glass, and would have to be kept off every seal and skin of the vessel indefinitely. The winds at that altitude circle the entire planet in 4 to 5 Earth days, a perpetual planet-wide river of storm called superrotation, in which the whole sky travels 60 times faster than the world beneath it turns. Below any failure of buoyancy waits the furnace, patient and total. And even this gentlest concept ends the way every Venus concept ends. The crew never lands, because there is nothing to land on that will not destroy them. They would float and observe and eventually leave, visitors to a world that can be approached forever and never quite arrived at. Even as a neighbor, Venus keeps a certain distance. Its closest approaches, near as they are, arrive only briefly. For most of its orbit, Venus actually stands farther from us than Mars does at its own best moments, because the two planets spend most of their years on opposite sides of the Sun. And the world itself hoards its mysteries behind the clouds. The surface has never once been seen in visible light from orbit. Everything we know of its continents and plains was drawn by radar, or seen by the armored landers in their final hours. High in the cloud decks, something absorbs half the ultraviolet light the planet receives, painting dark patterns across the white that have been watched for a century and never explained. On the night side, observers have reported a faint ashen glow, and instruments have hinted at lightning flickering inside the acid clouds, observations still debated on a world close enough to see with the naked eye from a suburban garden. The nearest planet is, in several honest respects, less known at its surface than worlds 10 times farther away. There is a last irony in Venus worth carrying as we leave it. Its gravity is about 90% of the Earth's, the only world in the Sun's family whose pull a human body would find truly familiar. Of all the planets, Venus alone could hold a settler's bones and heart at nearly their proper weight. The most familiar gravity in the solar system is wrapped around the least survivable surface in the solar system. The door fits our hand perfectly and opens onto fire. Even the planet's own rhythms refuse our habits. Venus turns backward, and so slowly that its day outlasts its year. The Sun, seen from the clouds, rises in the west, 4 Earth months between one dawn and the next. So the nearest planet defines the first complete answer to tonight's question. The journey to Venus is the easiest planetary journey there is, the shortest crossing, the most frequent windows, the gentlest homecoming, a round trip of barely a year that our grandparents' rockets could have flown. No one has succeeded because success has nowhere to stand. The crews who might have made that flyby would have watched an unbroken sheet of yellow-white cloud slide silently beneath them for a few hours, and then coasted home for months, having touched nothing at all. Venus is a destination without an arrival, and so we turn outward at last, away from the Sun, to the one planet where arrival is truly possible, and where every plan our species has ever drawn has aimed, the small red world next door. Part 6. Mars, the crossing. Mars is different from every other world in tonight's journey, and the difference is worth stating carefully. Mars is the only planet whose crewed journey has ever been engineered in full. For Mercury, there are no plans. For Venus, only the old flyby sketches. For the giants, nothing but whiteboards. But the journey to Mars has been designed again and again in generation after generation of studies, the ships drawn, the trajectories computed, the budgets estimated, the crew's daily schedules blocked out hour by hour. Whole shelves exist of Mars architectures, each one complete enough to build from. And none has ever been built. Mars is the most reachable planet, and the space between most reachable and reached is the truest measure we have of how hard planetary travel actually is. So we will give Mars the attention that gap deserves and take the journey in 2 parts, tonight's crossing and then the arrival, the stay and the way home. The crossing begins with the calendar. Earth and Mars arrange themselves correctly once every 26 months, and the window that opens then lasts only a few weeks. Everything about a Mars expedition flows backward from that fact. The ship must be finished, fueled, checked, and crewed against a date that celestial mechanics chose years in advance and will not move. If a valve fails in the wrong month, if a booster is late, if a crew member falls ill in the final weeks, the mission does not slip a season. It slips 26 months, all at once, while the propellant boils slowly away and the budgets age. More than one robotic mission has missed its window and waited out the full cycle on the ground. A crewed program would wait the same way, at a cost measured in careers. When the window opens and the burn is made, the ship settles onto its long ellipse, and the crossing proper begins. 6 to 9 months of coasting, depending on the year's geometry and the mission's appetite for propellant. It is worth pausing on what those months actually contain, because the popular imagination fills them with drama, and the truth is quieter and stranger. Nothing happens. The engines are silent. The Earth shrinks to a bright star behind. Mars is a dim ember ahead, growing so slowly that no eye could notice a day's change. The ship falls, perfectly, along the curve chosen for it months before, and the crew lives inside the falling, exercising against the slow theft of their bones, tending the machines that scrub their air, watching the sun for storms, and waiting. The most eventful moments of the entire crossing are a handful of correction burns, gentle nudges of a few meters per second, computed from radio ranging and starlight, each one closing the aim a little tighter. The margins are unforgiving in their own quiet way. A correction of a few meters per second, weeks from arrival, is the difference between threading the top of the Martian atmosphere and missing the planet entirely. But they are moments of stillness, not fire. A Mars crossing is not an adventure. It is a half-year of discipline, performed inside the clocks we met earlier in the night, every one of which is running. The radiation clock runs fastest. From the day the ship leaves the Earth's magnetic shelter, the cosmic ray rain falls through it, roughly a millisievert a day, every day, outbound and homebound alike. The mission designs answer with the storm shelter, the small refuge in the ship's core, walled with water tanks and food stores, where the crew would wait out a solar eruption. The steady background, though, cannot be sheltered from. It can only be endured and counted. By the time a crew completed the standard round trip, the dose from the crossings alone would approach or pass the lifetime allowance professional crews are permitted today, before a single day spent on the surface is added. Radiation does not forbid the journey to Mars. It forbids the second journey, and mission planning has quietly absorbed that fact. For any crew flying chemical rockets, Mars is a once-in-a-lifetime road. The weightlessness clock runs just behind it. 6 to 9 months of freefall is at the edge of what station crews routinely endure, and the comparison flatters the crossing falsely, because a station crew's ordeal ends at home. Theirs ends at Mars. The crew will arrive with bones measurably lighter, muscles wasted despite the daily hours on the exercise machines, hearts smaller, balance gone, and no one waiting to carry them from the capsule. Within minutes of first feeling weight again, they must fly the most difficult landing in the solar system, and within days they must labor like a construction crew. Planners have a sober name for this period. They call the first days after landing the most dangerous of the whole architecture. Not because Mars attacks, Mars does nothing, but because the crossing has already spent the crew, and the mission's hardest work is stacked precisely where the crew is weakest. The obvious remedy is to cross faster, and the rocket equation prices it without sentiment. Trimming the outbound leg from 6 months to 4 roughly doubles or triples the mass that must leave the Earth, because the harder departure burn and the harder arrival braking both compound. Trimming it to weeks belongs to nuclear engines that have run on test stands but never flown with a crew. So the architectures accept the slow road, and the slow road sets the scale of everything. Every ton that is to be landed on Mars requires 7 to 10 tons lifted into Earth orbit first. Propellant, stages, shielding, stores, which is why every serious plan begins not with a launch, but with a shipyard. Hundreds of tons assembled in orbit across dozens of launches and years of work before any crew departs. The largest structure ever built in space, the station, took more than 40 launches and over a decade to assemble, and it never had to go anywhere. A Mars ship is a project of that size that must then leave. And the crossing's total, both directions summed, presses against the edge of everything medicine knows. The longest any human has ever remained in space without a break is about 14 months. A standard Mars round trip roughly doubles that figure, with a landing, a gravity well, and 500 days of expedition labor set in the middle of it. Every table of physiological data our species owns simply ends, well before the mission would. And beneath both clocks lies the fact that separates a Mars crossing from every voyage in human history. From the day of departure, there is no way home but forward. A station crew is minutes from an emergency return. A lunar crew was 3 days. A Mars crew, from the moment of the departure burn, cannot come home early at any price, because home is no longer a place behind them. It is a moving target that will only be reachable again when the orbits realign. If the mission plan says the stay is 500 days, the stay is 500 days. The ship's orbit owns the itinerary. Illness does not shorten it. Grief does not shorten it. Even abandoning the landing entirely and remaining in orbit does not shorten it. Celestial Mechanics is the mission commander, and it has never once granted a request. The Solitude has a texture that mission studies describe with unusual care. The radio delay to Mars runs from about 4 minutes to 24, each way, depending on the two planets' positions. Somewhere in the first weeks of the crossing, conversation with the Earth quietly dies, not in a moment of drama, but in lengthening pauses, until the crew stops waiting for answers, and the voices from home become letters, recorded and replied to like correspondence from another century. And once every 26 months, the geometry adds a deeper silence. Mars and its travelers pass behind the Sun as seen from the Earth, and for roughly 2 weeks, the Sun's roar swallows the radio link entirely. A crew in transit or on the surface during solar conjunction is, for those weeks, as alone as any humans have ever been, out of sight, out of contact, on the far side of the star that lights both worlds, trusted to keep themselves alive on stores and judgment until the sky opens again. That is the outbound crossing, and every kilometer of it must eventually be flown again, in reverse, by a crew a year older, carrying a dose already counted, aboard a ship that has weathered years without a harbor. The crossing, in the end, is the tax Mars charges twice. What waits between the two payments? The landing that has never been performed at crude scale, the 500 days of surface exile, and the one machine no one has ever built, the rocket that leaves, is where the journey to Mars has always, truly, come apart. That is where we go next. Part 7. Mars. Arrival, the stay, and the way home. The journey to Mars comes apart, historically and technically, not in the crossing but at the far end, in 3 problems stacked one atop another, each unsolved at the scale a crew requires. The first is getting down. The second is staying alive for 500 days. The third, the deepest of all, is the one almost no one outside mission planning ever thinks about: getting back up. Getting down first. Mars wears the most inconvenient atmosphere in the solar system, about 1% the density of the Earth's, and that thin shroud is exactly wrong in both directions. It is thick enough that a ship arriving at interplanetary speed, near 6 kilometers per second, will burn without a heat shield. It is far too thin to slow a heavy ship to landing speed. At the Earth, the air does nearly all the work of arrival. Capsules fall, glow, slow, and drift down under parachutes with hardly a drop of propellant spent. At the Moon, there is no air at all, and engines do everything, which at lunar gravity they comfortably can. Mars offers the worst of both: heat without help. Parachutes that would float a capsule gently home barely whisper in Martian air. Even the largest ever flown, opened at supersonic speed, serve only to trim the fall before rockets must take over. Every landing ever made on Mars has threaded this needle with a different piece of ingenuity. Airbags, sky cranes, throttled descent engines, and every one of them shares 2 humbling features. Each sequence, from the top of the atmosphere to the ground, lasts about 7 minutes and must run entirely on its own. The radio delay means the landing is over, one way or the other, before the Earth even learns it has begun. And each has landed, at most, about 1 ton. That is the record. A machine the weight of a small car, lowered on cables by a hovering rocket stage in a sequence of pyrotechnic events that all had to fire perfectly, in order, with no rehearsal and no second chance. A crude lander, with people, seats, shielding, supplies, and the machinery of survival, is estimated at 20 to 40 tons. 20 to 40 times beyond everything ever demonstrated. The only known way to land such a mass is supersonic retropropulsion, lighting engines directly into a hypersonic headwind and riding the thrust down. Reusable boosters on Earth have shown the trick can work in principle. No vehicle has ever attempted it in Martian air. When people ask, casually, Why we have not simply flown to Mars yet? This is among the truest short answers, because nothing the size of a cruise ship has ever been landed there, and the landing has no small-scale rehearsal. The first full test at crude scale will have a crew aboard, or it will have to be flown, complete and perfect, by an empty ship first, which is precisely what current plans intend. Suppose the landing succeeds. Now the Sun takes over the schedule, because the length of the stay is not a choice, it is a consequence of orbits. The geometry of Earth and Mars offers exactly two shapes of mission, with nothing between. In the short version, the crew stays 30 to 90 days, then accepts a punishing return, a trajectory that swings inward past Venus, lengthening the time in deep space and its radiation until the total round trip saves little and costs more. In the long version, the one nearly every modern architecture chooses, the crew must remain on Mars about 500 days, waiting for the two planets to swing back into agreement, and the whole expedition runs roughly 2.5 to 3 years door to door. 500 days is not a visit. It is an exile with a fixed term, a stay longer than most polar expeditions in history, on a world where the air is unbreathable, the water is buried, and the resupply time is measured in years. Mars will spend those days testing the camp, gently and without pause. Its gravity is about 38% of the Earth's, enough to make work feel like work, and an entirely unknown quantity to human biology. No person has ever lived in partial gravity long enough to learn whether the bones hold. Its thin air blocks almost none of the cosmic rain, so the habitats bury themselves under meters of soil, and the crew's dose keeps counting even on the ground. Its dust is finer than talc, laced with reactive perchlorate salts, and it works into seals and joints and lungs. Keeping it out of the living space across 500 days of coming and going is an unsolved problem of fine detail, the kind that never makes headlines and quietly dominates engineering reviews. Its storms in some years swell to swallow the entire planet, dimming the sky for weeks and starving solar power at the exact moment the crew most needs light and heat. Nights fall below -80. And through all of it, every machine, the air plant, the water plant, the suits, the rovers, the greenhouse, must keep working, because the nearest spare part that is not already on Mars is 2 years away. The landings themselves must also learn a new precision. Robotic arrival ellipses have shrunk over the generations from targets hundreds of kilometers long to a few kilometers across, a magnificent improvement, and still 2 orders short of what a crewed campaign demands. Because a crewed campaign is not one landing, it is a fleet of them, cargo ships, power plants, habitats, and the crew's own vessel, and every one of them must set down within walking distance of the rest. A habitat that lands 50 kilometers from its power supply has not landed badly. It has failed entirely, on a world where 50 kilometers on foot, in a suit, is a distance no one has ever survived. Some planners weighing all of this have proposed skipping the surface at first, orbiting Mars instead, operating rovers below with almost no delay, visiting the 2 small moons whose gravity is so slight that landing on them is closer to docking with them. The idea has never caught the public imagination, and it answers the title's question in its own way. Even the cautious version of Mars is a 3-year voyage no one has yet flown. And then the crew must do the one thing no machine in the entire history of spaceflight has ever done. No object placed on the surface of Mars has ever been launched off of it again. Not a probe, not a canister, not a gram of dust. Every mission to Mars, for all its brilliance, has been one way. The return has always been the missing half of the journey, and the reason is our old companion, the rocket equation, now compounded to its cruelest form. To carry a fully fueled ascent rocket to Mars, a mission must haul that rocket and its propellant across the crossing and down through the landing, mass multiplying mass at every stage until the totals leave the possible. So the favored architectures cut the knot with a manufacturing plan. Make the fuel on Mars. The chemistry is old and settled. Take the planet's carbon dioxide, air, and buried ice, apply power, and produce methane and oxygen. At the benchtop, it simply works. At mission scale, it means a nuclear-powered chemical plant landed years ahead of the crew, running unattended through Martian winters and dust seasons, processing tons of atmosphere day after day for roughly a year, filling the tanks of an ascent vehicle that stands empty on the plain, waiting, all before the crew ever leaves the Earth. The crew launches only when the telemetry says their ride home is already full. Even then, one more threshold remains. The ascent vehicle does not fly to the Earth. It flies to Mars orbit, where the return ship waits, and the two must find each other and dock, a rendezvous around another planet, with a 20-minute radio delay to home, performed by a crew 500 days tired. Around the Moon, a rendezvous failure had rescue options measured in days. Around Mars, there are none at any price. Mission designers do not dwell on the scenario, because there is nothing to design for it. That is the honest anatomy of the journey to Mars. A landing never demonstrated at scale, a stay that biology has never rehearsed, and an ascent that has never been performed by anything. None of the three is forbidden by physics. All three are unforgiving of the smallest failure, and they must all succeed, in sequence, twice 26 months apart. When people say we could go to Mars, they are right. When the plans keep sliding a decade at a time, this is why. The most reachable planet is guarded not by one wall but by three, and the tallest of them faces the sky of Mars, not the sky of home. Beyond Mars, though, the walls change character entirely, because past the little red world, the solar system stops being measured in months at all. And that is the threshold we cross next. Part 8. The Great Gap, where the solar system changes its units. We have come a long way already tonight, and this is a natural place to pause and let the journey so far settle into order. We began at the true high water mark of human travel, the far side of the Moon, 400,000 kilometers out, reached by 24 people for a few days each, more than a generation ago. We learned the price of leaving, the exponential arithmetic of the rocket equation, the long unpowered ellipses of the transfer orbits, and the windows that open on the planet's calendars rather than ours. We learned the price of enduring, the radiation clock, the slow dissolving of bone, the pantry that can never quite be closed, and the silence that replaces the Earth's voice a few weeks out. Then we spent those prices 3 times. At Mercury, the journey itself is the wall, the deepest road in the solar system, 7 years of falling for a world of lead-melting noon and ancient polar ice. At Venus, the journey is easy, and the arrival is impossible, the nearest world, wrapped in a furnace with no floor for a footstep. At Mars, the journey, the landing, the stay, and the return are each almost possible, and it is the almost, stacked 4 layers deep, that has kept every crew at home. If you have been drifting, you have missed nothing that the night will not gently repeat. Every planet so far has refused us in its own particular way, and each refusal has taught us the shape of the next. Now the story changes scale, and it changes honestly. Between Mars and Jupiter, the solar system does something the maps never quite convey. It opens. The distance from the Sun out to Mars, the entire theater of every journey we have discussed tonight, is about 228 million kilometers. The distance from Mars out to Jupiter is more than twice that span again. Everything inward of this line is measured in months. Everything beyond it is measured in years, and the tools that make inner planet travel imaginable begin, one by one, to fail. The first thing to fail is sunlight. Every crewed vehicle ever flown has run on the sun, panels drinking light, batteries carrying the shadowed hours. But light thins with the square of distance, and the arithmetic turns quickly cruel. At Jupiter, sunlight arrives 27 times fainter than at the Earth. A high noon there resembles the deep twilight of a winter evening at home. At Saturn, the light is 90 times fainter. At Neptune, 900, a brilliant star that casts shadows but no warmth. Past the asteroid belt, solar panels grow from wings into fields. Past Saturn, they become gestures. The robotic travelers out there run instead on the steady warmth of decaying plutonium, generators with no moving parts that have whispered power for decades, including aboard the two old probes still calling home from beyond the planets. But those generators yield hundreds of watts, the draw of a microwave oven, for an entire spacecraft. A crewed ship needs hundreds of kilowatts before the first instrument switches on. Air machines, water machines, heat, light, the greenhouse, the pumps. In all that darkness, there is exactly one candidate to supply it: a nuclear reactor, flown in space, rated to keep human beings alive for a decade without a service call. No such machine has ever flown. Every crude concept for the outer solar system begins with a power plant that does not exist. The second thing to fail is the pantry arithmetic. We priced a Mars round trip at tens of tons of consumables and strained the recycling loops to carry it. Stretch the mission from 3 years to 8 or 12 or 15, and the arithmetic simply exceeds what any ship can carry. An outer planet crew cannot bring enough. They must grow, recycle, and repair in a loop closed more tightly than anything ever demonstrated, for longer than any machine of any kind has run in space without maintenance from the Earth. The studies know this, and their pages fill with the honest vocabulary of the unsolved. Regenerative agriculture never proven in flight. Hibernation and torpor never attempted beyond surgical timescales. Rationing margins no agency would sign. The outer solar system does not merely lengthen the journey. It demands a sealed, self-repairing world, and we have never built one. The third thing to fail is the conversation. At Jupiter, the one-way radio delay runs 35 to 50 minutes. At Saturn, over an hour. At Neptune, about 4 hours. Mission control, that constant, murmuring presence that has watched over every crew since the beginning, becomes a diary exchange. A medical emergency near Jupiter is diagnosed, treated, and resolved, one way or the other, before the Earth's advice can possibly arrive. A crew out there is not supported from home. It is remembered from home. Every operational decision, every repair, every judgment call belongs to the people in the hull, entirely, for years. And one more quiet subtraction. Beyond Mars, there are no free returns worth the name. The forgiving loops that could sling a lunar crew home, the Venus flyby that flew itself, the geometry offers nothing so kind out here. From the moment of a Jupiter departure burn, a crew's only road home is another burn, years later, that simply must work. Even the sky itself grows less kind with distance, in a way few of the maps mention. The sun's magnetic field fills the whole planetary system like a great breathing bubble, and that field deflects a portion of the galactic cosmic rays before they ever reach the inner worlds. Travel outward, and the sun's protection thins behind you. The cosmic rain we first measured on the road to Mars falls slightly harder at Jupiter, harder again at Saturn, hardest of all in the far dark, where the sun's influence fades toward the interstellar wind. The outer solar system is not only darker and colder and farther from help. It is, measurably, less sheltered, the one shield no crew ever has to carry, slowly lowered, kilometer by kilometer, as the journey proceeds. And time works against the machinery in a second, subtler way. The plutonium generators that power the deep space probes fade as their fuel decays, a predictable dimming, 1% or 2% each year, that mission planners budget like a slow leak. The great probes of the outer system have spent their late decades switching off instruments one by one, rationing a warmth that can only diminish. A crewed ship on a 15-year voyage would age the same way, in 100 quiet places at once. Seals, bearings, filters, memory, fuel. The design problem of the outer solar system is not surviving a moment of drama. It is surviving the slow, patient arithmetic of decay, everywhere, for a decade, with no dry dock nearer than the inner worlds. And yet one thing about the Great Gap, contrary to every instinct and most illustrations, does not fail, and it is worth setting right before we cross. The asteroid belt is not a barrier. The pictures lie to us here more than almost anywhere. They show a rattling corridor of tumbling stone, hull close and hazardous. The truth is emptiness. The belt's entire mass amounts to a small fraction of the moon's, and a third of that sits in a single dwarf planet. The rest is scattered through a ring so wide that the typical spacing between sizable bodies is around 1 million kilometers, more than twice the distance from the Earth to the Moon, between one rock and its nearest neighbor. Probes cross the belt without evasive maneuvers of any kind. Several have crossed it while actively hunting for a single asteroid near enough to photograph, and found the search difficult. If the whole belt were swept together and reassembled, it would make a body far smaller than the Moon. A crew crossing it would see, in all likelihood, nothing at all, just the same star-salted black as everywhere else, for month after month. The belt matters to the journey not as an obstacle, but as a milestone, the last landmark before the years of coasting begin, the place where the solar system's units quietly change from months to years, from kilowatts to whispers, from conversation to correspondence. Beyond it waits the first of the giants, the largest world the sun ever made, guarded by the deadliest sky in the solar system, offering years of journey toward a destination with no ground at all. Let's cross the gap, slowly, and meet it. Part 9. Jupiter, years out and nowhere to stand. The journey to Jupiter is the first in tonight's story that must be measured in years, no matter how it is flown. The gentle road, the minimum energy ellipse, takes about 2 years and 9 months, one way. The probes that have actually made the trip, threading the limits of their launch vehicles with borrowed speed from planetary flybys, have mostly taken 5 to 6 years. For a crew, even the most optimistic version means multiple years in deep space in each direction, beyond every record of continuous human spaceflight before the destination is even reached, with all 5 clocks from earlier in the night running the entire way, the dose accumulating, the bones lightening, the pantry emptying, the voices from home stretching into month-old letters carried on a signal 3/4 of an hour long. And at the end of those years, Jupiter offers a refusal no world so far tonight has offered. Mercury at least has ground, however scorched. Venus has ground, however lethal. Mars has ground that a crew could genuinely work. Jupiter has no ground at all. The planet is a world of hydrogen and helium, 11 times the width of the Earth, and beneath its cloud tops there is no floor anywhere. The gas simply thickens as it descends, from cloud to haze to fluid, until, tens of thousands of kilometers down, hydrogen itself is pressed into a strange shining liquid that conducts electricity like metal. Nowhere in all that depth is there a surface, no rock, no ocean top, no boundary a landing gear could ever touch. A crewed landing on Jupiter is not difficult. It is meaningless, a category error, like asking to land on a thunderstorm. Any descent, crewed or robotic, becomes a one-way passage. One small probe has made the trip, released by its mothership to fall into the clouds. It punched into the atmosphere at greater speed than any object our species has ever flown into anything, survived deceleration that would have pulped a human body many times over, and then drifted downward under a parachute through alien weather, reporting faithfully as it went. It lasted about an hour. Somewhere beneath it, in heat rising past the surface temperature of stars' outer skins and pressure climbing beyond any ocean floor, its transmitters failed, its parachutes sublimed, its metals softened, and it dissolved, its atoms joining the circulation of the planet, where they remain tonight, part of the weather of Jupiter. Every future entry vehicle, whatever its engineering, inherits the same ending. Jupiter does not keep visitors. It keeps their atoms. For the same reason, no sample of Jupiter will likely ever rest in a laboratory on Earth. Nothing that goes down into that gravity and that heat has any road back up. The giant can be measured, sounded, and mapped from a distance, but never held. Even hovering at the cloud tops, the science fiction compromise fails on the plain numbers. Gravity up there runs about 2.5 times the Earth's. A crew member who could somehow stand on a platform among those clouds would carry their own body weight again, and half once more, pressing down through their bones, indefinitely. The planet's interior pours out heat left over from its formation, driving winds of hundreds of kilometers per hour, and storms older than written history, the Great Red One among them, a single storm wider than the Earth that has been churning for at least centuries with nothing solid beneath it to slow it down. There is no still air at Jupiter, no calm harbor, and never, at any depth, in any season, anywhere to stand. But the deepest reason no crew has ever been proposed for Jupiter's neighborhood is invisible, and it surrounds the planet like a fortress wall. Jupiter's magnetic field is the strongest of any planets, some 20,000 times the Earth's in total strength, and it inflates around the planet into the largest coherent structure in the solar system, a magnetic province so large that if it glowed in visible light, it would hang in our night sky several times the width of the full moon. Within that province, the field does what magnetic fields do. It traps charged particles, hoards them, and whips them to furious energies, century after century. The result is a set of radiation belts that are, outside the Sun itself, the deadliest environment the solar system possesses. The innermost of Jupiter's great moons orbits inside a flood of charged particles, fed partly by its own volcanoes, a ring of plasma along its orbit that spacecraft engineers discuss the way workers discuss the interior of a particle accelerator. As we explored on a recent evening in this channel's tour among Jupiter's moons, the dose rates near the inner system would overwhelm an unshielded human being in less than a single day, and even the hardened electronics of robotic orbiters are rationed there, their close passes budgeted orbit by orbit, like radiation workers' shifts, each approach spending a known fraction of the machine's lifetime allowance. For any crewed mission, that wall redraws the entire map. The approach must swing wide of the inner magnetosphere. The orbits must hide in the calmer outskirts. The only destinations are the moons, the 4 great worlds and their dozens of small companions, the only flaws Jupiter offers, and even among the moons, the choice is dictated not by wonder but by dosimetry. The innermost are forbidden districts, and only the outer ones offer ground where machines, and perhaps someday people buried beneath meters of ice, could endure. Jupiter itself is forever a view. The largest world the Sun ever made can be orbited, studied, photographed from a cautious distance, and never, in any meaningful sense, visited. Then comes the bill for leaving. Jupiter's gravity well is the deepest of any planets. Escape from its cloud tops would demand about 60 kilometers per second, more than 5 times the escape speed of the Earth. And while no ship would ever fly from the cloud tops, every ship that breaks into orbit anywhere in the system must eventually climb back out of a well deeper than any other in the Sun's family. The propellant for that climb must either ride along for years or be found among the moons. The years home must be crossed again, with the ship older, the crew wearier, and the pantry thinner. The rare studies that have priced a crude Jupiter system round-trip land on figures of 6 to 12 years, door to door, durations at which the radiation total, the bone loss, the food mass, and the psychology stop being engineering margins and become the central facts of the mission. No agency has ever advanced such a mission past the whiteboard. There is a certain honesty in that restraint. The journey is not impossible. It is simply longer than any promise an institution knows how to keep. And yet, in the solar system's dry sense of humor, Jupiter is also the most helpful world in the entire story of travel. Nearly every journey to the planets beyond has been shaped by whether Jupiter happened to be standing where its gravity could be borrowed. A ship that sweeps close behind the giant leaves with kilometers per second of stolen speed, years shaved from its crossing, at no cost in propellant at all. The slingshot past Jupiter is the standard price of admission to the deep outer system. When Jupiter is out of position, Saturn and everything beyond recede by extra years, and whole missions wait on the ground for the giant to come around again. The wall and the doorway are the same planet. Jupiter forbids arrival and enables passage, the solar system's sternest gatekeeper, waving travelers through to destinations it will never permit anyone to reach within its own borders. So Jupiter's answer to the title is the strangest yet. The journey can be survived, perhaps, but it arrives nowhere. Years of crossing, a fortress of invisible radiation, a planet with no floor, and a return climb out of the deepest well there is, all for a destination that must, in the end, be admired through glass. The probes will keep going in our place, as they have for 2 generations, and the planet most visited by our machines may well be among the last ever visited in person. And still, the strange truth of the outer solar system is that Jupiter is the near neighbor, the first giant, the closest of the far worlds. Twice as far again, out in light 1% as strong as ours, waits a planet that repeats every one of Jupiter's refusals and adds, on one cold orange moon, the single gentlest landing the outer solar system will ever offer. That is where we go next. Part 10. Saturn, the decade round trip. Saturn stands roughly twice as far from the Sun as Jupiter does, and that single doubling is decisive for everything that follows. The gentle road to Saturn runs about 6 years, one way. The one spacecraft that has ever orbited it took nearly 7, and it could not fly anything like a straight line. To gather the speed its rockets could not afford, it swung twice past Venus, once past the Earth, and finally past Jupiter, each encounter lending a little of a planet's motion, the long way around the inner solar system in order to be thrown at the outer. Consider what that pattern of borrowing means for a crew. A crewed round trip to Saturn, in any propulsion generation now foreseeable, is a commitment of 10 to 15 years, no longer a mission in any traditional sense, but an era of a human life spent inside a hull. A crew member who left at 35 would come home at 50. The word expedition begins to fail somewhere past Jupiter. At Saturn, the honest word is closer to emigration, with a distant promise of return. The environment out there rewrites the engineering from the first page. At Saturn's distance, sunlight has thinned to about 1% of what falls on the Earth, permanent deep twilight, 90 times too faint for the solar wings that have powered every crewed vehicle in history. Only nuclear power remains, the reactor that has never flown, now asked to run faultlessly for a decade. The cold stops being weather and becomes a property of matter itself. Lubricants, seals, batteries, and plastics, all living beyond the edges of their tested ranges. The ship an island of warmth in a sea that will accept any heat it leaks and return none of it. And the conversation with home, already a correspondence at Jupiter, stretches further still, 68 to 84 minutes each way, depending on the season of the orbits. A question radioed to the Earth at the start of a quiet evening watch is answered, at the earliest, near its end. No landing, no docking, no emergency anywhere in Saturn's neighborhood can involve the Earth in real time. Whatever happens there happens among the crew alone, with home reduced to a wise but very distant diary. Saturn itself repeats Jupiter's great refusal. It is a gas giant, smaller than Jupiter, but built on the same plan, and it has no surface anywhere, the same deepening hydrogen, the same absence of any flaw, the same one-way dissolution awaiting anything that descends. Its gravity near the cloud tops is, curiously, close to the Earth's. Saturn is enormous but airy, the least dense planet of all, light enough that it would float in a sufficiently large sea, but familiar gravity wrapped around bottomless gas is no kindness. And Saturn adds one hazard all its own, the most beautiful obstacle in the solar system, the rings. From a distance, they look solid, a sheet of pale gold. Up close, they dissolve into what they are, countless orbiting fragments of nearly pure water ice, from dust grains to boulders the size of houses, each on its own path, 10 billion snowballs sharing a plane thinner, in proportion, than a sheet of paper. No ship plows through that. Arriving spacecraft cross the ring plane only at chosen gaps, threading gaps in the ice the way a ship threads a charted reef. The one orbiter, in its final months, dove 22 times through the narrow corridor between the innermost ring and the cloud tops, a passage no machine had ever flown, and even that ended, deliberately, with the ship surrendered to the planet, dissolved like everything else that descends. But Saturn, alone among the giants, holds a genuine door, and it is the strangest door in the solar system. Its largest moon, Titan, is wrapped in an atmosphere, a deep nitrogen sky, half again denser than the Earth's at the surface, the only substantial atmosphere possessed by any moon anywhere. And that thick, cold air transforms the hardest problem in spaceflight into the easiest. Landing, the ordeal that at Mars demands 7 autonomous minutes of pyrotechnics and hovering rockets, becomes, at Titan, almost restful. The air is deep and the gravity gentle, so an arriving craft slows softly, high up, and then simply descends. One small probe has done it. Released from the Saturn orbiter, it fell into that orange haze and drifted downward under parachute for 2.5 hours, the longest, slowest, calmest landing in the history of space exploration, settling at last onto a plain of rounded ice pebbles beside drainage channels carved by rain. Its photographs from beneath the haze look, at first glance, like a stony riverbed on Earth at dusk. It transmitted from the surface for over an hour, longer than anything has ever managed on Venus, on a world nearly 10 times farther away. Titan extends its strange hospitality further still. The pressure at its surface is half again our own. No pressure suit required, only warmth and air. Unique beyond Earth, a person's unprotected skin there would not boil and would not burst, but merely freeze. And in that dense air and 1/7 gravity, human beings could fly. Strap wings to a person's arms on Titan, and muscle power alone would lift them, the oldest dream in the human catalogue, waiting, fully licensed by physics, on the one world too far away to collect it. For a sleeping listener, this is perhaps the image of the night, the solar system's kindest landing, its gentlest air, its one offer of flight, placed a decade of travel from home. Because everything else about Titan is the far side of the ledger. The surface waits at about -180 degrees Celsius, cold enough that water ice is bedrock. The stones of that riverbed are frozen water, hard as granite, and the rain that carved the channels is liquid methane, falling slowly through the thick air in drops that drift down like snow. A suit there is not armor against vacuum, but a shell against cold that would pull the warmth from a body in minutes. Noon under the haze is a dim orange twilight, the sun a pale smear that never sharpens. And Titan orbits Saturn, which means every one of Saturn's numbers stands between it and us. The 6 to 7 year crossing, the reactor that does not exist, the decade of life signed away, the spares for the spares for the spares. The pattern of the whole episode sharpens here into its cleanest form. The solar system's kindest doors hang at the ends of its longest hallways. Mars, with its brutal landing, is 3 years round trip. Titan, with its gentle one, is 15. Titan is not even the system's only temptation. Closer in orbits a small, bright moon of ice, Enceladus, whose south polar fractures vent the contents of a buried ocean directly into space. Geysers of salted water and organic dust, rising hundreds of kilometers, feeding one of Saturn's faint outer rings. A lander there could sample an alien ocean without drilling a meter, simply by standing under the falling spray. But Enceladus keeps harder company than Titan. No atmosphere to ease a landing, a higher radiation neighborhood, and a deeper propellant bill to reach its orbit. The system that holds the outer solar system's gentlest door holds its most tantalizing one a few doors down, and both hang on the same 15-year hallway. The calendar, too, plays by outer system rules here. Saturn's launch windows in the earthly sense come round nearly every year, but the windows that matter are Jupiter's. Without the giant's slingshot, the crossing stretches by years, and the alignments that place Jupiter correctly on the road to Saturn recur only every couple of decades. Miss one, and the mission does not slip a season. It slips into the next generation of engineers. And a decade-class voyage collides with a quieter limit. Almost no component ever flown with crews has a design life near 10 years. A Saturn ship must be its own dry dock, carrying not only spares, but the tools to make spares, and the crew must include, in effect, its own shipyard trades, because the warranty on everything aboard will expire mid-journey, somewhere past the asteroid belt, with the nearest replacement part 6 years behind them. So Saturn's answer to the title is a bargain no institution has ever accepted, the finest destination in the outer solar system, at the price of the crew's middle years. And still, the solar system is not finished raising its price. Beyond Saturn, the distances double again, and out there, the journey stops costing years and begins, without exaggeration, to cost lifetimes. The last 2 planets are waiting, and we should go while the night is deep. Part 11. Uranus and Neptune, the lifetime voyages. Beyond Saturn, the numbers stop describing journeys and begin describing lifetimes, and this is the part of the night where the thumbnail's quiet promise comes due. Uranus orbits about 19 times farther from the Sun than the Earth does. Neptune orbits 30 times farther. Written as kilometers, the figures go numb. Nearly 3 billion, nearly 4.5 billion, so let the calendar say it instead. One spacecraft, and only one, has ever visited either world. It was flying the fastest outbound road ever flown, with the great planetary alignment of a century helping it along, borrowing speed from giant after giant. It reached Uranus after 8.5 years of travel. It reached Neptune after 12. And it could not stop. That is the detail worth holding gently, because it says everything about the edge of our reach. Stopping at a planet, breaking from interstellar-bound speed into a quiet orbit, costs propellant on the same scale as the original departure from Earth, and no rocket that could be launched could carry it that far. So the one ship that has ever seen Uranus and Neptune up close swept past each of them in a matter of hours. It photographed continuously, as each world swelled ahead and shrank behind. Its cameras, starved for light 900 times dimmer than ours, needed exposures so long that the entire spacecraft turned slowly to track its targets, a pirouette executed alone, 12 years from the nearest human hand. Then each encounter ended, and the ship flew on into the dark, as it still does tonight, beyond the planets entirely. Nearly every close-up image our species owns of the 2 outermost planets, every poster, every textbook plate, every blue marble of Neptune, was gathered in those few brief afternoons, decades ago, in passing. Since then, no machine has returned. It is not for lack of wanting. The two ice giants are, by wide agreement, among the most scientifically valuable unvisited places in the solar system, worlds of a class our galaxy seems to build more often than any other. The obstacle is the arithmetic of a working life. Orbiter concepts for Uranus and Neptune, robotic, uncrewed, the modest version of the dream, are planned around cruises of 12 to 15 years, after the years of design and construction, before the years of operation. The teams are chosen young, deliberately, so that the engineers who launch the ship will still be working when it arrives. Mission documents speak, in their dry way, about knowledge retention and generational handover, meaning, in plain language, that the people who build the ship must teach it to successors who will meet it at the far end. Some of the builders will retire before arrival. Some will not live to see it. That sentence, more than any dose rate or delta V figure tonight, is the honest answer to the title's question. At Uranus and Neptune, even the robots' journeys are measured against human mortality, and the mission plans budget for it, in careers, the way inner-planet missions budget for propellant. Now let the crude version stand in that light, briefly, because no agency ever has. Extrapolated from any near-term propulsion, a crude round trip to Neptune runs 25 to 30 years or more. A crew member departing at 30 comes home at 60. The middle of a human life, the years of raising children, of burying parents, of every ordinary richness, spent inside a hull the size of a house, in darkness 900 times deeper than daylight, on food carried or grown, beyond rescue and beyond conversation, with home a 4-hour-old voice. There is no crude mission concept for either ice giant, not even on paper, and the reason is not engineering pessimism. It is that the mission profile stops being a plan and becomes a biography, and no institution has ever known how to ask for one. The worlds at the end of these unwalked roads keep the family pattern of refusal, each in its own strange key. Both are ice giants, smaller than Jupiter and Saturn, built not mainly of hydrogen, but of deep slushy mantles of water, ammonia, and methane, wrapped in hydrogen skies, and neither has any surface. The same bottomless descent, the same absence of anywhere to stand. Neptune, the farthest planet of all, is not the quietest but the wildest. Its winds are the fastest ever measured on any world, up to about 2,000 kilometers per hour, 5 times a hurricane's worst. Driven by an internal warmth no one has fully explained, the planet radiates roughly 2.5 times the heat it receives from its distant sun, glowing gently from within like a banked fire. Uranus, nearer and stranger, radiates almost none, the coldest upper atmosphere ever measured on a planet, despite Neptune lying half again farther out. The difference between the twins is one of the outer system's standing open questions. And Uranus adds its signature oddity, familiar to this channel from an earlier evening. It lies tipped fully on its side, rolling around its orbit like a barrel, each pole taking its turn pointed at the sun for 21 years of daylight, followed by 21 of night. A lander at the wrong latitude, on a moon, since the planet itself offers no landing, would face decades of continuous darkness before its first sunrise. Mission planners must choose hemispheres, knowing the seasons outlast the spacecraft. Even the moons out here tell travel stories with lifetimes folded inside them. Neptune's great companion Triton is a world nearly the size of Pluto that Neptune did not make. It circles backwards, against its planet's spin, the sure signature of a body captured whole from the belt of ice worlds beyond, long ago. It is slowly spiraling inward, and in a distant epoch will be torn into a ring. In the meantime, it is one of the coldest places ever measured, nitrogen frost at about -235 degrees, and yet it is not still. The one passing spacecraft photographed geysers of nitrogen gas erupting through the frost, lofting dark plumes kilometers high into an atmosphere 70,000 times thinner than ours, where they bent downwind and drifted, smoke in a near vacuum, weather at the edge of nothing. A crew that somehow crossed the 30 years of dark would stand, at journey's end, on frost that erupts, under a sun that gives light without heat, a brilliant star casting sharp shadows and no warmth at all, on the most beautiful and least reachable ground in the sun's whole family. The roads themselves are rationed too, by the same gatekeeper as always. A slingshot past Jupiter shortens the crossing to either ice giant by years, but Jupiter stands correctly on the road to Neptune only about once every 13 years, miss the alignment, and the whole enterprise defers for most of a further decade. Breaking at the far end remains the unsolved half. The energy needed to settle into Neptune orbit rivals the energy of the original departure from Earth, and the only studied shortcut, aerocapture, a single deliberate pass through Neptune's own atmosphere to shed the speed, has never been attempted by any spacecraft at any planet. The first try, if it ever comes, will happen 4 light hours from help, on a maneuver where the corridor between capturing and burning is a few dozen kilometers wide, at the end of a 15-year approach that allows no second pass. And beneath all of it lies the blankest page in the file. No human has ever lived long enough in spaceflight conditions for medicine to say what 30 years would do. The dose tables, the bone curves, the psychology studies, every data set our species owns runs out before the outbound leg would end. The medical textbook for such a voyage does not exist and could only be written by the voyage itself, on its crew. And the 4-hour silence would govern everything. At Neptune's distance, a radio question needs about 4 hours to reach the Earth, and the answer needs 4 hours to return. A probe breaking into orbit there performs its one critical burn entirely alone. The Earth learns of success or failure 8 hours after the matter has been settled. For a crew, the arithmetic is the same and heavier. Every emergency out there begins, unfolds, and ends, is survived or is not, long before home even knows it happened. The listener drifting towards sleep can hold the whole situation in one image. Somewhere out there tonight, Neptune is blue and roaring in the dark, and if we called out to it right now, the fastest thing in the universe would not finish the round trip before you wake. So the outermost planets answer the title's question with the simplest arithmetic of the night. The journey takes a lifetime, not as a figure of speech, but as an entry in the mission ledger. And with that, we have visited them all. 7 worlds, 7 refusals, each different, none final. What remains, before sleep, is to gather the reasons into one quiet accounting, and to ask what, if anything, could ever change them. Part 12. Why no one has succeeded yet, and what it would take. The title of tonight's journey asked a single question, and the honest finding of the night is that it has no single answer. It has 5, and they stand stacked, each one behind the last, so that solving any one of them alone changes nothing. It is worth laying them side by side, quietly, now that we have seen them all at work, because seen together, in a single view, they explain a century of plans that were drawn in earnest and never flown. The first answer is physics. Chemical rockets, the only engines ever trusted with human lives, sit at the bottom of an exponential curve. Their exhaust leaves at a fixed, modest speed, and every additional demand of velocity multiplies, rather than adds to, the ship. The round trip to any planet requires velocity budgets that turn a cruise vessel into hundreds or thousands of tons at departure, assembled over years by fleets of launches, all before the journey has moved a meter. Physics does not say no. It says everything you have, and then most of it again, and it says it at every planet, twice. The second answer is biology. A human body in deep space runs down its clocks, the radiation dose accumulating toward lifetime limits within a single round trip, the bones dissolving month by month, the eyes reshaping, the heart softening, the pantry emptying. The journeys are measured in years, and the body's tolerances are measured in months. Every mission design is an attempt to fit the second number around the first, and for every world past the moon, the fit has never quite closed. The third answer is engineering, the specific machines that do not yet exist. The closed life support loop that can run for years without resupply. The crew-rated space reactor for the dark beyond the asteroid belt. The 40-ton lander for a world with 1% of an atmosphere. The ascent vehicle that lifts from another planet's ground, fueled by a chemical plant that ran alone for a year before its crew ever left the Earth. Not one of these is forbidden by any law of nature. Not one has ever been built. Each is a decade of patient work, and they are all needed at once. The fourth answer is the calendar of institutions. A planetary expedition consumes 10 or 20 years of a spacefaring civilization's discretionary effort, design, assembly, rehearsal, flight, while the horizons of budgets and governments turn over every few. The missions outlast the promises that fund them. This is the least romantic wall of the four, and it has stopped more journeys than radiation ever has. The plans do not fail. They simply outlive their sponsors, and are shelved, and are drawn again a generation later, a little better each time. And the fifth answer, the quiet one, is that the robots have been magnificent. Every planet in the Sun's family has been visited, flown past, and in most cases orbited, and at Mars and Venus and Titan landed upon, by machines that need no food, feel no dose, fear no decade of silence, and grieve no separation from home. The probes have been our senses in every place our bodies cannot yet go, and they have been glorious value. For the cost of one crude voyage, a dozen robotic ones fly, each answering questions of its own. Whenever a crude journey is weighed, the same gentle alternative sits on the other side of the scale. Send the machine, keep the crew, learn nearly as much. It has been the winning argument for 2 generations, and the honest accounting of tonight must admit that it has usually been right. No one has traveled to a planet partly because, so far, no one has needed to. The solar system has been explored, by proxy, patiently, and well. There is a 6th observation, not quite a wall, that belongs in the accounting. Every breakthrough serves the robots first. The same nuclear engine that would carry a crew to Saturn in 3 years would carry an orbiter there in 1. The same closed-loop greenhouse that would feed a crew would extend a base's reach. The same reactor would power a fleet of probes. Whenever a new capability arrives, the case for waiting one more robot generation arrives with it, freshly strengthened, and it is always a reasonable case. The crewed journey must therefore be chosen, not derived, not forced by necessity, but chosen, in the way sailing ships once chose the open ocean when the sensible arguments all pointed home. That choice has simply not yet been made by anyone, and no law of physics can make it for us. None of these 5 walls is permanent, and the night should say so plainly. Nuclear thermal engines, twice the efficiency of chemical ones, have run on test stands. Nuclear electric propulsion could push heavy ships along faster roads, and every doubling of speed folds the map of the solar system in half. Artificial gravity by spin is physics any student can size, waiting only for structures large enough to swing. The recycling loops tighten year by year. Experimental greenhouses inch toward true regeneration. The water walls and buried habitats of the radiation answer are already drawn. The windows will keep opening. Mars every 26 months, Jupiter every 13, the great alignments on their long calendars, with perfect patience, forever. The walls are real, and every one of them is, in the long run, climbable. But the deepest finding of tonight is the one the thumbnail promised, and it deserves to be said once, gently and in full. The true currency of planetary travel is not money, and not propellant, and not even risk. It is time inside a human life. Count the journeys in birthdays as a traveler would. A flyby of Venus, one birthday spent aboard. Mars, there and back, with the surface exile between, 3. The system of Jupiter, 8 to 12. Saturn and the orange skies of Titan, 15. Neptune, blue and roaring at the edge of everything, 30. The entire middle of a life, traded for one arrival. Even a tenfold improvement in propulsion, a revolution beyond anything on any drawing board, leaves Neptune a 3-year round trip, longer than any human has ever flown. The solar system is not refusing us. It is simply built at a scale where a human life is the smallest unit of travel, the way a coin is the smallest unit of a currency, and every journey outward must be paid in whole coins, never in change. So the record stands where we found it at the start of the night. 24 people to the far side of the moon, a few days each, a generation ago, and no one farther. Not because the planets are unreachable, but because reaching them costs the one thing every traveler has exactly once. Perhaps the record will fall within the lifetimes of some who are listening tonight. The machines that would break it are, for the first time, being seriously built. Perhaps it will stand another generation, while the robots go on ahead, as they always have, carrying our questions where our bodies cannot follow. Either way, there is no failure in the accounting, only proportion. We have been counting in months and years and lifetimes all night, but the planets do not count that way. They have made their circuits for 4.5 billion years, and they will make them for billions more, whether we visit or not. Every journey we traced tonight, every window missed, every plan shelved, every decade deferred, has happened inside a single tick of their clock. They are not waiting impatiently. They are simply there, turning in the dark, keeping every road open. And that is, in the end, the gentlest possible answer to the question we began with. Why has no one succeeded yet? Because the solar system is immense, and life is brief, and our species has so far chosen, sensibly and a little sadly, to spend its brief lives at home and send its patience on ahead. The planets are not refusing us. They are simply far, in a way that makes a human life the smallest unit of the trip, and they have been patient for 4.5 billion years. They can be patient a while longer. Whatever distances you cross tonight, this is where they end. Here, in the warm and quiet near the sun, on the one world in all that dark, where no journey is required. Let your breathing slow. Let the miles unwind. Sleep well, and good night.